So in this chapter, and it's a little bit of a few different chapters, but we're going to really talk about a couple of things. We're going to talk about equations and balancing equations. Then we're going to talk about different ways to classify equations. We'll talk about double displacement reactions, we'll talk about redox reactions. We'll talk about oxidation numbers and stuff like that that goes with redox reactions. And we'll have a lab coming up where we'll talk about how to balance redox reactions in sort of acidic and basic conditions. So the first part of this we're going to start with is the balancing equations. So let's get into that. So obviously, when a chemical reaction occurs, that's really a chemical change. So what we start with and what we end with are fundamentally different things. And we represent that as a chemical equation. And there's really obviously a couple parts to a chemical equation. There are reactants, which are our starting material, and they go to products, which is obviously what is made as a result of a reaction. Remember that in a chemical reaction, really the only thing that's happening is we are breaking apart bonds on our reactants, and we're making new bonds on our product side. So there's no elements that are changing, and that's obviously really important for the balancing part of an equation. We start with 6 carbons, we should end with 6 carbons. They may be in different things, but we definitely do not lose any of those things along the way. Other things that we do see in a reaction is above the arrow, sometimes you may see a delta symbol. That usually refers to heat. Sometimes also above the arrow, you will find other things like catalysts are sometimes listed. So a catalyst could be like a metal, like platinum, could actually be like H+, which is an acid catalyst. Catalysts are not reactants. They are not products. They do not get used up in a chemical reaction. They're there just to facilitate that reaction occurring, in most cases, quicker. So it allows sort of an alternative pathway for those reactants to come together. And in most cases, it will usually result in the reaction speeding up in terms of how fast it occurs. So again, a catalyst there, not a reactant, not a product, and does not get used up. In the reaction. In addition, obviously, our reactants and our products, we also will oftentimes see the states of these guys written next to their formulas. So S is solid, L is liquid, obviously, G is gas. And a lot of times what we will see is AQ, which is our aqueous. And that basically is a water environment. That's really a solution. So, you know, all the sort of chemicals, if you use it in a lab, that basically comes out of dropper bottles, those are all aqueous. Those are all solutions that are made. In addition, sometimes energy or heat is put into an equation. We talked a little bit about sort of endothermic and exothermic and energy. If you have heat or energy put into an equation on the reactant side, it's an endothermic reaction, like it's gaining heat and energy. If you have heat and energy sort of put into the equation on the product side, it's an exothermic reaction, like it is being given off or being released. Most of the time, though, when we look at chemical reactions in terms of energy, it is that delta H, or that enthalpy that we talked a little bit about. Value that we oftentimes are given in a chemical equation or reaction. And again, a reminder, delta H is negative. It's exothermic heat and energy being given off. If delta H is positive, it is endothermic heat and energy being absorbed in that particular case. Any questions on that there? So we can look at an equation and we could read it a couple of different ways. We could say 2 atoms, in this case, a magnesium plus 1 molecule of oxygen forms 2 formula units of magnesium oxide. Now, formula units are sometimes used for ionic compounds. because they're technically not molecules. Also, we just talked about molar mass. So sometimes people will use formula weight or formula mass instead of molar mass for ionic compounds. It's essentially the same thing. It's calculated the same thing, but sometimes people will use that for ionic compounds because they're not sharing electrons, and it's more of an ionic bond rather than a covalent bond. The relationship, as we'll talk about in the next chapter or so, that we use a lot from an equation is the mole to mole relationship, is what we use in stoichiometry to do stoichiometry sort of calculations. And it does come from the coefficients. So that is what the 2 in front represents, 2 moles of magnesium. There's no number which represents 1. 1 mole of oxygen gives you 2 moles of magnesium oxide. The last one here is the conservation of mass. We don't lose nor create anything along the way in a chemical reaction. That's why we do have the conservation of the elements, which is 48.6 and 32, which are the molar masses of each of those guys. And since you should have the same elements on the back end of the reaction, you should have the same molar mass there on the back end, which is at 80.6. The only relationship that we cannot get is obviously a gram to gram relationship. So we do not have that relationship that comes from that equation. So balancing equation is really important. There's several sort of steps to balancing equations. The first thing that you want to do is make sure that you have all the proper formulas given to you. Sometimes you may be given everything in words and not formulas. So you need to make sure that you translate them into the proper formulas first. And what that means is you should not balance and write formulas together. And it's a common problem that people have when they go to write products, if they're just given reactants and they have to kind of predict what's on the product side of the arrow. A lot of times they will write formulas and try to balance it at the same time. And you do not want to do that because you'll get the wrong formulas and the thing will never balance in most cases. The proper steps of that is you want to write the proper formulas first and then balance it. So you want to write the proper formulas like you were doing, like nomenclature and that type of thing, get all the proper formulas down. Then you should go back and balance it. Basically, to balance an equation, once we have the proper formulas, the only thing that we change are the coefficients. So we only change the numbers that come in front. We never change any of the subscripts. We never change any numbers in between. Because if we change the 2, for example, there, that's a subscript, that is no longer carbon dioxide. We change it to something else, right? So it's only the numbers in front. We basically want to continue adding coefficients until we have the same number of elements on both sides, atoms of those elements on both sides. Sometimes you might want to start with the most complicated. Some people say sometimes it's easier just to start with the easiest thing that's just sort of fixed. Most of the time, as you put coefficients, what will happen, as you may know, is you'll screw up the balancing of other things and you got to put some more coefficients. But if you do it correctly, everything should balance out and come together correctly. When you are all done with your equation, there's got to be basically 2 things that happen. You need to have all whole numbers for the coefficients. And they need to be the simplest set of whole numbers. So what that means is if you balance the equation by putting a 2 and like a 4, and maybe you had a 6. In this particular case, although it may be balanced, this equation, you can go through and reduce down all those coefficients by 2 in this case. And that is what you would want to do, which would give you A plus 2B gives you 3C. And that would be the properly balanced equation. And this does occur sometimes because people could see perhaps larger numbers to balance things, and it could definitely be balanced with the greater numbers as well. But when you do balance the equation, it does need to be the simplest, smallest set of whole numbers to balance it for it to be balanced properly. And those really are the 2 sort of major things when you go to balance it. Personally, when I go to balance an equation, I personally like to make a table. And if we do, we'll rewrite this guy here, C2H6 plus O2, CO2 plus some water. So if you make like a table of all your elements, carbon, hydrogen, and oxygen in this case, reactant side, product side, On the reactant side there, we have 2 carbons. On the product side, we have 1 carbon. Reactant side, we have 6 hydrogens and 2. Oxygen on the left there is 2, and we do have 3 oxygens, 2 in the first guy and 1 in the second, which gives us 3. So personally, I would start with what looks like the easiest thing to fix and balance. And in this case, carbon looks pretty simple. To put carbon balance, we do need to put a coefficient in front of it, which would be a 2. That's going to give us on the product side 2 carbons. Hydrogens, we still have 2. Oxygens, we do multiply this 2 to everybody behind it. So that would give us 4 oxygens there, plus 1 more, gives us 5. So we did fix the carbon. We're still a little bit of issues with some other ones. Personally, I'm going to go with hydrogen next. The reason I'm not going with oxygen is oxygen's in multiple things on the right-hand side, and hydrogen is just in one thing on each side. So it makes it a lot easier to balance. So to fix the hydrogen, we're going to go with a 3 in front of it. When we do so, again, we have 2 carbons. 3 times 2 is 6 hydrogens. Now, in terms of our oxygens, 2 times 2 is 4, and 3 times 1 is 3. That does give us 7 oxygens in this particular case. At this point, we want to balance the oxygens. We definitely don't want to change the numbers on the right. Otherwise, you get into a never-ending cycle of racing and adding numbers. So really, the only place where oxygen is on the left is right here. And we basically need to turn our 2 into a 7. And to do this, the way that we can do it is we could actually use a fraction. So you can use a fraction to balance an equation. And if we use a fraction, say something like 7/2, seems like a good one. Now, when I do that, I end up with 2 carbons. I have 6 hydrogens, and when I take 7/2 times 2, they cancel, gives me 7 oxygens in this particular case. I am balanced. Am I correctly balanced, though, in terms of an equation? I am not. Although you can definitely use a fraction to balance an equation, you cannot leave it. So you do have to clear the fraction. And in this case, to clear the fraction, what we would want to do is multiply everybody by the denominator. So in this case, we would take everybody here, and we would multiply everybody by 2. And I'll get a little bit of room. And if we do that, we end up with 2C2H6 plus 7O2 and 4CO2 and 12 waters. And if you do that correctly, we should still be balanced. And we can look at it. We got 4 carbons on the left. We also have 4 on the right. We have 2 times 6, which is 12 hydrogens on the left, 12 on the right. 7 times 2 is 14 oxygens. And we have 8 in the first one and 12 there in the second one. I'm really doing bad with math today. I know I should get the calculator out. Let's try that. That should be a 6 would look much better on that there. There we go. Try again. Let's see. 2 times 3 is 6, I think, is what they say. All right, try that again. 6. There we go. All right. So 6 times 2 is 12 hydrogens, and we have 8 oxygens, and 6 is much better there, 14 in this case. There we go. So that will give us our properly balanced equation. Obviously, if you multiply 2 correctly, it would be much better. Any questions on their balancing? So absolutely, you can use a fraction to balance it. Just got to make sure that you clear it at the end. The formula for how to pick the proper fraction is super easy. The top number is the number you need. So if you remember, we needed a 7. The bottom number should match the guy there, and you'll always have the right fraction. So top number, what you need, bottom number should match the subscript, and you'll always have the right fraction that you need to use. Any questions on that there? All right, so why don't you try some here for professionality's sake? Sure. All right, so why don't you balance this equation up, see what you come up with. Okay, let's take a look and see. So once again, if we kind of make up a table here, NOH, reactant side, product side, we got 1 nitrogen on the left, 2 on the right. We got 1 oxygen on the left, 1 on the right, 2 hydrogens on the left, and 2 on the right. So everything's really balanced here except for nitrogen. So clearly that seems like a good place to start. We'll put a 2 in front of it on the left. That gives us 2 nitrogens. In terms of oxygen, we also multiply the 2 by that, gives us 2, and we still have 2. So much like what happens, we will fix one thing, kind of screw up something else. So in this case, we now should go to our oxygen on the right, and we need a 2 there, it looks like. And that will give us still 2 nitrogens. That will give us 2 times 1, which is 2 oxygens, and 4 hydrogens. Again, each of those coefficients go for everybody behind it. And in this case, now we just need to go back to the hydrogen and put a 2 there, and we should be in business. That would be 2 nitrogens, 2 oxygens, and 4 hydrogens in this case. And we would be balanced. Yeah. Any questions on that one there? All right, so let's take a look at a couple more here. Just make sure. All right, so balance up this guy here. All right, so let's take a look. We got carbon, hydrogen, and oxygen. We have reactants, we have products. So we have 3 carbons on the left, we have 1 on the right, 8 hydrogens on the left, 2 on the right, and oxygens 2 on the left, and we do have 3 on the right, again 2 there and 1 more over here. So again here, carbon is probably the easiest. We're going to do a 3 in front of it on the right. That gives us 3 carbons. We still have 2 hydrogens, and in terms of oxygen, we have 6 in the first one, and 1 more makes 7. Once again, here I'm going to go to hydrogen since it's all kind of 1 and 1, not oxygen, which is in a lot of places. So to fix the hydrogen in this case, 4 would be a good spot. Going to give us 3 carbons, 8 hydrogens. We now have 6 oxygens there, and 4 more there makes 10 in this case. So to fix that, we can now go to the left-hand side. Gives us 10 oxygens, still 8, and still 3. And now we are balanced. Yes. Any questions on that one there? All right. All right, so balance this guy up here. This is one where we do have some words. So remember that, as I mentioned, you want to make sure you get the right formulas first and then balance it. So the correct formulas there: diboron trioxide is a type 3 compound, B2O3. Water is H2O, and then boric acid in that case there, BOH3. Okay, let's take a look. We got boron, oxygen, hydrogen. So we got 2 on the left and 1 on the right. We got 3 and 4 oxygens on the left. And we do multiply this guy into everybody that's there. So that would be 3 oxygens there on the right. And on the left there, we have 2 hydrogens. And on the right, we also would have 3. This case, not a lot to work with. So we will start with the boron, which would be a 2. That's going to give us 2 borons. We also multiply the 3 in, and we do also multiply it to the guy on the outside as well. So that's going to give us 6 for the oxygen and also 6 for the hydrogen in this case. That means that we're going to go with hydrogen next. Once again, oxygen's in multiple places here. So for our hydrogen, we would need a 3 to balance it on that side. That's going to give us 2 borons. Oxygen, 3 and 3 is 6, and hydrogen is 6. So by actually just balancing the hydrogen in this case, it did take care of actually the oxygen as well. Any questions on that one there? All right, a couple more here. All right, balance this guy up, see what you get here. All right, let's take a look here. So we have 1 nitrogen on the left, 1 on the right. We got 2 oxygens on the left and also 2 on the right. And hydrogen, we got 3 on the left and 2 on the right. So everything's balanced except for hydrogen in this case. So common number between 3 and 2 is 6. So we'll put a number on the left and right in this case. We'll go a 2 here and a 3 there to get each of those hydrogens to 6. That gives us 2 nitrogens on the left. That gives us 2 oxygens, and it gives us 6 hydrogens. On the right-hand side, we still have 1 nitrogen. Oxygen, we have 4 now, 1 in the first one and 3 in the second. And hydrogens, we have 6. So we kind of fixed hydrogen, but really screwed up everything else. Again, the probably easier thing to balance at this point is going to be the nitrogens, as it's only in one place on each side. So we're going to do a 2 over here. That gives us a 2 nitrogens. That gives us 2 oxygens in the first one and 3 more there. Gives us 5. And we have 6 hydrogens in this case. We again now have everything balanced except for the oxygen, which is in a couple places on the right and 1 place on the left. So this again is a good place to use a fraction to balance this equation. Now we need to turn basically our 2 into a 5. So remember, when you do the fraction, the number on top is the number you need, which is a 5. Number on the bottom should match that guy, which is a 2. And in this case, we would then end up with 2 nitrogens. We would have 5 halves times 2 is 5 oxygens, and 3 times 2 is 6 hydrogens. Again, we are technically balanced, but we cannot leave the fraction. So although we can use it again to balance it, we do have to take the extra step if you do not want it marked wrong. Yes, and multiply everybody by 2. And that would get you 4NH3 plus 5O2 gives us 4NO plus 6 this time, I think, waters. And again, at this point, we should still be balanced. We have 4 nitrogens on each side. We got 12 hydrogens on each side, and we have 10 oxygens on each side. So we are balanced. Any questions on that there? So if you're struggling and things aren't balancing, perhaps a fraction might be helpful, but just make sure that you do clear it when it's all said and done. Now, let's take a look at these couple of equations here. Now, sometimes when you go to balance equations, you might have some equations that have a lot of those polyatomic ions in it. And a lot of times when you have polyatomic ions into an equation that you want to balance, it is a lot easier to kind of keep those polyatomic ions together rather than going sort of element by element. You can go element by element, but there's a lot more sort of multiplying in because there's usually parentheses and numbers that you have to multiply. So for example, if we look at the top one here, we have phosphate there, we have phosphate there, we also have carbonate in each of these cases. So if I were to balance this, I would actually balance it based on the phosphate, and I have 2 phosphates on the left, I have just 1 on the right. So I would balance the phosphate by putting a 2 in front of it. The method of this means that wherever you put that number to balance out, in this case, the phosphate, it will also tell us where we need to go next. And that is where we should go next, which is the sodium also changes. So the sodium becomes a 6. So that is where we want to go to next to balance it to the left-hand side. And to get our sodium to a 6, we would need a 3. Although we went for the sodium here, that also then made our carbonate 3, which means we would finish it up by bringing in a 3 over here to balance out the carbonate. That also takes care of the iron as well. So you're in business pretty quickly. It is usually a lot quicker and maybe a lot less room for error when you do have polyatomic guys on both sides of an equation, just to keep them together and sort of balance them as units. Any questions on that there? Lastly, if we look at this last example here, we have sulfate on both sides in this case. We also have hydroxide on both sides in this case. And here I will start with the sulfate. I got 1 on the left and 3 on the right. So to fix that, I'll put a 3. Because I fixed the sulfate, I did mess up the silver. So that's where I want to go next, which is 6. To get silver to 6, we would put a 6 there. That then gives me 6 hydroxides, which means I need a 2. And we will end up with a balanced equation. Now, if you happen to have maybe chose wrong here, in a sense of polyatomic ion, since you did have a couple of ones to choose from. So let's just say you decided to start with the hydroxide and went with 3. When that gave you the silver would also be 3, you would know that that's maybe not the right choice, and you would have to, again, go back and sort of fix it at that point. You could probably figure out that you would need 6 of those, and you could adjust it and then end up with the same thing. So even if you kind of chose wrong, you could just start with the other polyatomic ion, and it would probably work out okay if you ran into an issue like that. Any questions on balancing? It is really important that whenever you're using an equation, either straight up a balancing equation, it should be balanced, or if you're using it for calculations like we do in stoichiometry, you should always check the equation to make sure that it is balanced. I would say that if you see coefficients in the equation, it probably is balanced. But if you don't see coefficients, and even if you do see coefficients, you should check it to make sure. All right. The next thing we're going to talk about then is electrolytes. And there's a few different types of electrolytes. There are strong electrolytes, there's weak electrolytes, and there's non-electrolytes. And an electrolyte is really a substance that when it goes for a swim in water will break apart into ions. And it's actually the presence of those positively charged and negatively charged ions that help kind of conduct electricity. Kind of completes the circuit, all that good stuff, and allows the electricity basically to flow. A non-electrolyte is a substance that will dissolve, but will not produce any ions. So you will not get any electricity sort of being conducted. If you have a non-electrolyte, it will look like that. If you kind of hook up a light bulb to some electrodes and put it into a non-electrolyte solution, no electricity, light bulb stays off. If you have a weak electrolyte with the light bulb sort of example there, it will conduct a little bit of electricity. So light bulb will come on. It will look a little bit dim, like it's kind of dying. And if you have a strong electrolyte, as you can see, the light bulb will shine very, very brightly because there is a lot of ions in solution. So a strong electrolyte, for example, is something that will, as I mentioned, will 100% break apart into ions. So something like sodium chloride, which a solution of sodium chloride. In solution, it is 100% sodium ions and chloride ions floating around in that solution. And because there is a lot of free ions floating around that solution, it's going to be able to conduct electricity really, really well. It would be like the light bulb we just saw there going off very, very brightly. Strong acids like hydrochloric acid is a strong electrolyte like H plus and Cl minus. In solution, you have 100% of these guys in there. Strong bases, a lot of strong bases are guys that contain hydroxide. And group 1 and 2 on the periodic table are our strong bases, because the word alkaline means basic, and that's our alkali metals and our alkaline earth metals. So those guys with hydroxide are guys that make really strong bases. That is going to be a sodium ion, and a hydroxide ion will 100% break apart. And all these guys, if you have solutions of them, pretty much any ionic compound will also be pretty much a strong electrolyte, will 100% conduct electricity really, really well. In terms of acids, and we'll see it a little bit later on as well, in terms of strong acids, there's a few that you should know as you go through your chemistry life. HCl is a strong acid. Nitric acid is a strong acid. Sulfuric acid is a strong acid. Hydrobromic acid is a strong acid. Hydroiodic acid is a strong acid. And perchloric acid is a strong acid. So these kind of 6 guys are really strong acids. They're strong electrolytes. And if you see something that is not one of those 6 and is an acid, it's probably a pretty safe bet that it's going to be a weak acid, which is a weak electrolyte as well. So these strong electrolytes, nothing stays together. Everything completely breaks apart, conducts electricity really, really well. And that is different than a weak electrolyte. A weak electrolyte will mainly stay together, but will break apart, will produce a few ions. So weak acids like hydrofluoric acid is a weak acid. When it goes for a swim, it will break apart into H plus and F minus. But in solution, you mainly have the HF unit still together. But you do have a few of these guys floating around. So when you look at like the beaker, it's mainly HF floating around in there together. But you do have a little bit of F minus and H plus floating around. And because it's still able to produce a few ions, it's still able to conduct electricity. And because it's able to conduct electricity, it will be a little bit dimmer though, because of the fewer amount of ions that are present. The way you can recognize a weak electrolyte is usually there are the arrows that head in both directions. That means it's a reversible reaction. And when we have a reversible reaction, there is a forward direction and there is a reverse direction. The forward direction is reactants going to products. And what happens is at some point, you will produce enough products that it will go back the other way. They will actually go back and produce some more reactants. It will eventually reach what is referred to as chemical equilibrium, which does not mean you have the same amount on each side. But when it reaches chemical equilibrium, what that means is the rate of the forward direction will equal the rate of the reverse direction. So essentially, as quick as it breaks apart into products, those products will recombine and make more reactants. What that does is not give you necessarily the same amount of reactants and products on both sides of the arrow, but it locks everybody into place as to where they were at when it reached equilibrium. Because if it goes back and forth at the same rate, you're pretty much not changing very much on either side of the arrow. They're going to basically maintain their concentrations, or if you're talking about gases, they will maintain their pressures at that pretty much that point. HF is a weak acid. Acetic acid, also a weak acid. HCN is a weak acid. There's a number of weak acids. Like I said before, a lot of weak acids are weak electrolytes. And pretty much if you kind of remember those 6 that we just mentioned on the previous slide that were strong acids, pretty much anything else will probably fall into that weak acid sort of situation. Now, a non-electrolyte will dissolve in solution, but it will not produce any ions. And it's really that lack of ions in the solution, which is why it will not conduct electricity. So because you're not producing any ions, it will basically not be able to conduct electricity. So sugar is an example. Sugar is basically carbons, hydrogens, and oxygens. Those guys are going to be covalently bonded together. If you have some solid sugar, it definitely will dissolve in water, but it will not produce any ions. So it will not basically conduct electricity. So it's really the presence of ions in solutions that help conduct electricity, which makes something a good electrolyte. That is why when you have pure water, good or bad conductor of electricity? Pure water is a bad conductor of electricity, pure H2O. By the way, the water that comes out of your pipes is not pure water, and you will electrocute yourself if you blow dry your hair in the shower. They actually put ions into your water to purify them and clean them and stuff. So there's lots of ions that come out of tap water and stuff like that, which is why you can get electrocuted, obviously, using that water. But if you have basically just H2O by itself, it has no ions floating around in it. It technically would be a bad conductor of electricity. Yeah. Water softener is completely different because water has ions in it, positive 2 charged ions like calcium and stuff like that in water. So what a water purifier does, or water softener actually does, is you throw salt in there like sodium, which is a +1 charge. So it softens your water in the sense of taking out all those highly charged calciums. So it usually goes through like a matrix in the tub, and it's ion exchange basically. So the strongly charged +2 jumps out of the water. It's attracted to the softener part of it, and it's exchanged with sodium in your water. That helps obviously your pipes, right? So it doesn't get all corroded and stuff like that with the strongly charged calcium, stuff like that. So that's how basically a water softener works. You're basically popping out the strongly charged or highly charged positive guys with lower sodium, or an alternative sodium. If you can't have sodium in your diet, if you put a lot of sodium into your water, you don't want to do that either. So they have some alternatives for that, but it's actually the lower charge that does that. Other questions? All right, so as we mentioned here, are things that do conduct electricity are strong electrolytes. Pretty much none of it stays together. Definitely going to conduct electricity. That's acetic acid. There was sort of a question that somebody asked me the other day about sort of formulas, and acetic acid is very common, and acetate as well. This is acetic acid, and that is the formula for acetic acid, but sometimes they will just give you the sort of baseline formula of C2H4O2. And that basically just tells you what's in acetic acid. This is more of a structural formula for acetic acid, that if you were to draw the Lewis structure for it, it looks something like this. So sometimes you will see formulas that will give you a little bit more of a structure based of how they're put together, which is what this formula does, versus this one, which just kind of tells you what is present, but they are the same thing. And this kind of depends on what formula somebody uses to describe it. But we do see our reversible arrows here. And again, that implies it's going to be a weak electrolyte, still able to produce a little bit of acetate and H+, so it will conduct electricity. You're going to get your dim light bulb in that pretty much situation there. Now, this sort of opposites and how things sort of dissolve into water is sometimes referred to as the process of hydration. And especially when we have an ionic compound that's been dissolved in water, it will basically get surrounded by water, and water is polar, as we talked about when we talked about bonding. And it is the oxygen side of water that's more negative. It is the hydrogen side is more positive, as the dipole moment is right there. And that is pretty much how ions get surrounded and dissolve. Ionic compounds dissolve in water. The positive ion, as we can see here, is attracted to the negatively charged oxygens. So all the negatively charged oxygens for water basically surrounds the positive ion, while the negatively charged anion is attracted to the hydrogen side of water, which is the white circles there in the diagram, which is the more positive side of water. This does two things. The attraction between the ions, the positive ion and the negative ion, is a super strong attraction, strongest you could have. But there is such a great quantity of water in water, obviously, when you poured something into it, that there's enough waters that they actually can rip them apart from each other, the ions, and surround them. And it keeps those ions from coming back together, right? Because what would happen if we took a solution like this and heated it? All the water would evaporate, right? And on both sides, all the water would evaporate, and that would allow those ions to come back together, and you would have your solid. Kind of similar to what we did in the last experiment, where you had all that water, right? And the final step was to throw it up there, evaporate off all the water until you had just your solid residue left over. Same idea. By evaporating off the water, that allows nothing to sort of buffer out the ions, and they're going to come back together, back into their solid sort of version at that particular point. So that's the process of hydration when we do dissolve something. This is a table kind of similar to what you have in your book, but here are some strong electrolytes. These are some of our strong acids. These are some of our strong bases, and any ionic compound will 100% break apart. These are some of the weak acids and a weak base, which is ammonia there. And those guys will break apart a little bit, but mainly stay together. So this is a one-way arrow, everybody breaking apart. That is a two-way arrow, people staying together, breaking apart a little bit. This is a one-way arrow with no ions, which is our non-electrolytes. So these are some non-electrolyte solutions, which are basically covalently bonded together. So this all leads to really what's important in a certain type of reaction that we come across. And we're going to talk about now really a type of reaction which is known as a double displacement reaction. And really the double displacement reaction and the redox reaction are really the two big classification of reactions that you could have. And there are more specific ways to classify reactions that fall underneath each of those categories. So things like synthesis, combination, precipitation reactions, acid-base reactions, they fall under these umbrellas, but pretty much all reactions can be classified as pretty much one of these two types of reactions. Now, there's really three reasons why a reaction takes place. And the three reasons why a reaction takes place is for a solid to form or a precipitate, the formation of water, and the third one is an electron transfer. Pretty much all chemical reactions break down to one of these three things happening. For double displacement reactions, they take care of pretty much those first two things, solids being formed and water being formed. Everybody else pretty much falls to the redox sort of category, which is an electron being transferred. So we're going to first focus in on today here the double displacement reactions. Then later we will focus in on redox. But in a double displacement reaction, it basically has this general formula of AB plus CD. And these are two ionic compounds. And whenever you have two ionic compounds that come together, the two positive guys will switch partners. So the positive guy of one will go to the negative guy of the next. And we will end up with two new compounds on this side, which are ionic, A and D, and C and B. Now, as a result of these ion switching partners, one of these guys could make a solid, which is sometimes referred to as a precipitate. And that is a type of reaction known as a precipitation reaction, which is really a double displacement reaction, but a solid forms. Now, what could also happen is one of these guys may make water. And in that case, that is usually involves an acid and base reaction. And that's sometimes referred to as acid and base neutralization reaction because basically it made water. So the precipitate being formed or water being formed happen in either a precipitation reaction or acid-base reaction. Clearly, a precipitation reaction, you can see the precipitate being made. You cannot a lot of times see water being made, right? You pour it together and go, wow, I made water. It looks the same. So a lot of times you can't visually see water being made, but it is being made. And those are two of the three reasons why a reaction takes place. And those fall under really the big umbrella of double displacement reactions. Electron transfer and redox, we will get back to a little bit later on. So that brings us to solubility. And the maximum amount of solute that will dissolve in a given amount of solvent is how soluble something is. A solution is made up basically of two things. It's a solute and a solvent. The solute is typically the thing that's dissolved in the solvent. So a lot of times we use water as our solvent. So we'll dissolve an ionic compound in water and it will dissolve and it will make a solution. A solution is those guys that get the aqueous symbol. And again, two parts to a solution is the solute, which is the smaller part, and the solvent, which is the larger part. So let's first look at a precipitation reaction and kind of see what is going on here. So in a precipitation reaction, some type of solid is formed, and that is what is referred to as a precipitate. So in this particular case, we're taking two solutions. We're taking lead 2 nitrate, and we're adding it to sodium iodide. I know this is a double displacement reaction because that's a positive guy, that's a negative. That's a positive, that's a negative, which means that the positive lead will go and hook up with the negative iodide. The sodium will hook up with the nitrate, which is what happens on the other side of the equation. This equation here, which is the balance equation, this is what is referred to as the molecular equation, where we write everything just the way it is with the proper formulas, and we also have our states. What is really going on, though, in this solution when we mix everybody together is these things will not stay together. They will break apart because most of them are strong electrolytes. So we could write another equation to really describe what is happening in this reaction. And that is the first guy, which will break apart, is a strong electrolyte. We will have a lead with a +2 charge. We have 2 of the nitrates, which will break apart. So the 2 comes out in front. Our sodium iodide is also a strong electrolyte, so the 2 in front gets distributed to everybody behind it. Now we come to the right-hand side, and we do have a solid. In order for it to be a solid, both the positive guy and the negative guy has to be stuck together. And that means they will not come apart, right? If they did come apart, there would be no solid. So they have to actually be together so they stay together. So in this type of reaction, which is what we're writing right now, anything that is a solid, anything that is a pure liquid, anything that is a weak electrolyte should stay together. So you wouldn't break it apart. So we're not going to break apart the solid in this case. So we'll keep it together. But this sodium nitrate is an ionic compound and a strong electrolyte, and it will break apart into a couple of sodium ions. And I'm running out of room, so I'll go underneath, and a couple of nitrates as well. This equation here, which shows what's really happening in the beaker or test tube, is what is referred to as the total ionic equation. Or some people call it the complete ionic equation. It is an ionic equation, which means that you should have ions, which means it should have charges. So when you write these formulas, they should have charges because they are ions. And as I mentioned before, you do not break apart anything that's a solid, anything that's a liquid, anything that's a weak electrolyte, or a gas in most cases. So anything that's a solid, a liquid, a weak electrolyte, you stays together. Now, when we look at an equation like this, which is a total ionic equation or complete ionic equation, you should always be able to find ions on both sides of the arrow that look exactly the same. So if we look in this case, there are a couple of sodiums and a couple of a couple of nitrates. There are also a couple of sodiums on both sides of the arrow. These ions, which are exactly the same on both sides of the arrow, are what are referred to as spectator ions. Spectator ions are much like the name implies. If you are a spectator, you are just watching. They are not really doing anything that is going to lead to the product being formed. They're basically just there to balance out the charge of everybody. So they're just floating around the solution, having a good time, but they're not going to lead to the product being formed. So typically what we do with spectator ions is we scratch them out of the total ionic equation. And this leaves us the third type of equation, which is sometimes a really important equation. That is our lead plus our couple of iodides come together to make our PbI2 in this case. This is what is referred to as the net ionic equation. And the net ionic equation pretty much tells you exactly what is going on in this equation. What is really happening when we mix both of those solutions together is the lead ion that's floating around from the lead 2 nitrate is going to find the iodide ion that's floating around from the sodium iodide, and they're going to come together to make that solid, which in this case is that yellow solid that we see there, which is the lead 2 iodide. And that is the molecular equation, the total ionic equation, and the net ionic equation. And once again, that net ionic equation should also have charges to the ions that are there as well. Any questions on that? When you get to the total ionic equation and you cancel out your spectator ions, if you did it correctly, they should completely cancel out. So if you get to that part and it's like, I got 2 on one side and 1 on the other side, that probably means you did not balance the equation correctly. And you should go back and probably balance it up correctly. Any questions on that? So this is a precipitation reaction. You get a solid, and it is ultimately also a double displacement reaction, a more specific classification being a precipitation reaction. So how do we know if we mix two things together, will we get a solid or will we not get a solid? And we could actually use solubility rules to help us determine whether or not, if we put these two ions together, for example, should we expect a solid? So what we're looking at here on this table is the solubility rules for things that are typically soluble in water. And what that means is they are soluble in water. They are the things that will get the aqueous symbol. So if something is soluble based on solubility rules, it is aqueous. It is basically a solution. Everything should dissolve. It will just be a solution. Anything from group 1 on the periodic table, which is pretty much these guys here, are ammonium. They are going to be soluble in everything, which means if you see a chemical formula that contains anybody from group 1 are ammonium, you don't need to look any further. There's no exceptions. That thing should get the aqueous symbol. So it definitely should get the aqueous symbol if you have any of those. Nitrate and acetate, same deal. If you see nitrate or acetate in the formula for anything, you should know it's aqueous and it's going to be soluble. Chloride, bromide, and iodide, they are soluble in everything, but there are some exceptions. So what does that mean? It means that if you see chloride, bromide, and iodide in a formula, in most cases, it will be soluble and it should have an aqueous symbol. The only time they would not be soluble is if there was silver, that's mercury 1, and that is lead 2 that's in the formula. And if it happens to be one of those guys with chloride, bromide, or iodide, it would go from being aqueous to being insoluble, which means that you would make a solid, and it would get the solid symbol in that case. So none of those guys on the right, these guys will be aqueous. Anybody on the left there makes it insoluble, which would be a solid. Sulfate is also pretty much soluble in everything, except for silver, calcium, strontium, barium, and lead 2. So if you have any of those guys with sulfate, it goes the opposite way and they would be insoluble, which would get the solid symbol. Any questions on the solubility rule there? Now, we also have some solubility rules for things that are normally insoluble. So things on this list typically would be insoluble and get a solid next to it. So these guys typically would get a solid, and that is hydroxide. The only exceptions are pretty much what we saw on the previous slide. If you have any of these guys, they will be aqueous, which is basically group 1 in ammonium, which is the same thing as the previous slide. Calcium, strontium, and barium are slightly soluble. For the most part, slightly soluble. Usually most people lean it being more insoluble as being slightly soluble. Really anything is sort of has a little bit of solubility, but slightly soluble. It sort of leans more towards being insoluble. Sulfides are normally going to be solids, except if it's hooked up with any of these guys, and then it will be aqueous and be soluble. Carbonate and phosphate typically will be solid, and unless they're hooked up with these guys, then it would be aqueous in this case. Any questions on that there? So let's take a look at one here. So if we had something like let's do some sodium sulfide, put a 2 there. And let's do calcium chloride. Actually, let's not do calcium, bad choice. Let's do iron. All right, let's do iron 2 chloride. All right, I want you to write the products, use the solubility rules to determine the solubility of everybody, and then also write the total ionic equation, the net ionic equation, and ID the spectator ions. So complete the equation, complete the solubility, and write those 3 equations, see what you come up with. Look and see. So first off, when you're looking at this, you want to maybe identify what type of reaction you're dealing with. So this is an ionic compound, so that's a positive, negative. That's also positive, negative. So you should know that this is a double displacement reaction to begin with, which means our positive guys are going to switch partners. So in this particular case, our sodium will end up with our chloride. Our iron will end up with our sulfide here. When you do the formulas, as we talked about, you want to make sure that you get the correct formulas and then balance, not try to do them both together. That means that really in this case, we are taking the basic units of this, which is sodium and sulfide, and iron in this case is +2, and chloride. These are the basic ions that are going to be reshuffled correctly on the other side. That means when I take the sodium and the chloride, I get NaCl. I do not get Na2Cl2 because that is wrong. Yeah, so you want to take the basic thing here. I would then get the iron and the sulfide, which is +2 and -2, which means this is what I should get out. Any questions on that? Now that you have all the proper formulas, now you want to balance it. So in this case, I do need to put a 2 here for the sodium. And that also takes care of the chloride, I think. And we have 1 iron and 1 sulfur. So we are balanced in this case. First off, any questions on how to properly predict it on that side there? Now that we have the equation and it is balanced, we could use our solubility rules here to help us determine if these things are going to be aqueous or solid. When I look at the first one, I see sodium, and that is pretty much as far as I need to go because sodium is group 1, which means they are soluble in everything. And I know automatically that this guy should be aqueous because of that. Now, in this case, I look at iron. I may not find iron on my solubility table, but I will find chloride. And chloride is soluble in everything except silver, mercury, and lead, which this is not any of those. This is iron. So that is not any of those 3. And because it's soluble in everything except for those 3, it would also get the aqueous symbol because it is soluble. Coming to the other side, I got sodium, which is, again, as far as I need to go, really, because it's soluble in everything. And that would be aqueous. You could even look at the chloride. Chloride, again, is soluble in everything except for silver, lead, and mercury, which is not the case here. So we're good either way. Now, when I look at the sulfur, right? Sulfur is insoluble, right? Except for, we look at our little chart there. Sulfur is insoluble except for these guys. And iron is not on that, which means that that will produce a solid in this case. So that iron and that sulfur, when it comes together, will produce this solid because it is insoluble. Any questions on how to use solubility rules there? This is our balanced molecular equation. We can now write our total ionic equation. Since this first guy is ionic, it's going to break apart into 2 sodiums. And so 2 comes to the front, and 1 sulfide. The iron 2 chloride also ionic, which means it's a strong electrolyte. It will break apart into an iron with a +2 charge. The 2 comes in front of the chloride because we do not have Cl2 minus there. That is 2 Cl minuses. So again, very common, people will write something like this, which is not the case. You basically have the 2 in front because you have 2 of these guys basically floating around. We will go to the other side of the arrow where our sodium chloride will also break apart into 2 sodiums as that 2 gets distributed to both things behind it. And lastly, here we have our solid, which will stay together. Again, I ran out of room, so I'll just go underneath it. This is our total ionic equation. Any questions on that? Again, from your total ionic equation, you can identify your spectator ions. And in this case, it looks like it is the 2 sodiums on both sides of the arrow, and also our 2 chlorides. They are exactly the same on both sides. So those are our spectator ions. Getting rid of our spectator ions will leave us our net ionic equation, and our net ionic equation is the iron is going to find the sulfide, and it will make FeS, which would be our solid, and it is net ionic. If you balance the equation to begin with, when you get to your total ionic equation and your net ionic equation, they also should end up being balanced as well. So that's why it's really important to always start with a balanced equation and make sure you distribute those coefficients. Also make sure you distribute the 2's that are subscripts when you get to the total ionic equation. Any questions on that? Now, typically speaking, it is proper in most cases to write the positive guy first, then the negative guy in the net ionic equation. That is usually the way it kind of goes. It's not technically wrong. I wouldn't mark it wrong if you did it the other way, but most of the time you'll see the positive guy and then the negative guy going to our solid. Question on any of those 3 equations there, or how to use solubility rules here? All right. So obviously here, if we use our solubility rules, we see potassium, which tells us that this should be soluble. And this guy should have the aqueous symbol. We have silver bromide. Again, bromide is soluble in everything except for silver, lead, and mercury, which means that this would be insoluble in this case and get a solid. Calcium chloride, chloride soluble in everything except silver, lead, and mercury, which is not the case here. So this guy should be soluble, which gets the aqueous. We see nitrate, which is a good key because it's soluble in everything, which means this guy would be soluble. And lastly here, our lead 2 sulfate. In case you're not sure, we go to sulfate, which is soluble. Lead, though, is an exception. So even though it is normally soluble, because it is bound with lead in this case, it would be insoluble. That gives you a solid in terms of that. Any questions on that? All right, one last thing here. If you happen to have an equation that does have one of those weak electrolytes in it, so let's just say we had hydrofluoric acid, which is a weak acid, plus say sodium hydroxide, and this is a double displacement reaction that makes some sodium fluoride and some water here, H2O action. All right, so in this particular case, if we have this as our molecular equation and we wanted to write the total ionic equation, you would need to recognize that this acid is a weak electrolyte, which means it actually should stay together. We would not break it apart because it's a weak electrolyte. So unlike normal, where we would break that guy apart, we would actually keep it together. The sodium hydroxide is a strong base, which means it's a strong electrolyte. And the hydroxide would also break apart. Coming to the other side here, our sodium fluoride's ionic, which means it will break apart. And what about water, which is a liquid? Do I break it apart or keep it together? I should keep it together as it is a pure liquid. So this is what our total ionic equation will look like in this acid-base reaction, actually. And it's a little bit different than the other one. But we still do have perhaps a spectator ion. And in this case, the only spectator ion there is sodium. So sodium is our only spectator ion in this particular case. And we would do the same thing, and that would leave us a net ionic equation that will look a little bit different than the other ones. That looks something like this. And that again arises because we have that weak electrolyte that is still really in the solution floating around because it's going to stay together. So it's not going to completely break apart. So if you were to look at the beaker there, like I said before, you will definitely still have that HF still floating around in there because it won't completely break apart. It'll break apart a little bit, but pretty much will stay together. So when you do have a weak electrolyte involved in a sort of total ionic, net ionic sort of equation, you do get a slightly different equation that develops. And a lot of times you'll end up with a little bit less in terms of spectator ions because it actually will stay together rather than completely break apart. Any questions on that one there? All right, we will wrap it up there for lecturing for now.